So in the previous lecture, we have discussed about the emergence of cycles into the GNP graph model, which has the threshold is P is equal to 1 by N. And this P is equal to 1 by N is not a sharp threshold. That also we have discussed in the previous lecture. After that, we have discussed regarding the full connectivity. That means when the graph will be full connected. So SAT threshold for full connected graph is we have considered is 1 by 2 ln n upon n. So after seeing these two results, in this lecture we are going to discuss about some non-uniform model. So far we have considered the random graph GNP with which all vertices have the same expectation of the degree and showed that the degree concentrated close to expectation. However, the large graph occurring in the real world tend to have a power law degree distribution. That also we have seen. So far, a power law degree distribution is the function f of d, is the number of vertices of a degree with the d plotted as a function of d. This satisfies the condition that is c upon d power alpha, where c and alpha are constants. To generate such graph, there are f of d vertices of a degree d and choose uniformly at the random from the set of a graph with the degree distribution. So to establish such graph, we should fix with the f of d, which is a vertices of a degree d, and choose uniformly random from the set of graphs with that degree distribution. Clearly in this model, so this is a different kind of model we are talking about. The graph age are not depend on independent. So they are not dependent. So the graph age are independent, not independent. And this makes that random graphs harder to analyze. So it is very hard to analyze what is happening into this such type of graphs we have. But the question of where a phase transition is occur into such random graphs. So in the non-uniform graph models, when the phase transition is occur, that is interesting problem. With choosing the arbitrary degree distribution is given to us. So the main motivation or main concern about this lecture is we consider the when the random graph with the non-uniform degree distribution has a giant component. So our treatment in this lecture and will institute without providing a rigorous proof. So we are not giving you a rigorous proof for that, but we just gives you institution about that concept that when we have a given degree distribution, what will be the phase transition of a graph will have a giant component. So this problem is first dealt by a two person. Their names are Molly and Reed. They have addressed this issue. When the random graph with the non-degree distribution has a giant component. So let lambda I be the fraction of vertices of degree I. So lambda I is the number of vertices which have a degree I. Then, according to the Mullian read, the graph will have a giant component if and only if. So then there are there will be a giant component if and only if summation of I running from 0 to infinity I into I minus 2 into lambda I is positive. When this situation is occur, then a graph will have a giant component. To see this formula is correct, with considering the exploring the component of the graph starting from given seed vertex. So we'll start with the one vertex. It is known as a seed vertex. A degree is 0. Vertices do not occur except that the case where the vertex is seed. And if the degree is 1 is uncounted, that means when the degree is 1, that means it will connect with some another vertices. Then the treatment of exploring along with the edge into the vertex. So thus, we do not want the encounter too many degree 1 vertices. A degree 2 vertex is a natural that the vertex entered by one edge and left the another one. So there is no net increase in the size of the fortune. So vertices of a degree I is greater than 2 increased by 14 by I minus 2, and the vertex entered by this edge. Thus, so what we are vertex with I is greater than 2 increased by fortune I minus 2 vertices. The vertex is entered by one of its edge, and thus there are I minus 1 edges to a new vertices in the fortune of the net gain of I minus 2. So the I into lambda I in I into I minus 2 lambda I is a proportional probability of reaching the vertex I, and I minus 2 account of for increasing and the decreasing in the size of fortune when the degree I vertex is reached. So this all the things we have considering by applying this concept of Mullian reads into the GNP graph model, and we use PI is the probability of the vertex has degree I. So we're fixing this PI as the probability of the vertex degree I. That means it is analog to lambda I. What is lambda I? We have denoted it is the fraction of the vertices of the degree I. So it is analog to this. So it turns out that the summation that is this condition I running from 0 to n I into I minus 2 into pi gives the value of precisely when P is equal to 1 by n, and the point at which the phase transition occurs. So at P equal to 1 by n, the average degree of each vertices is 1, and there are n minus 2 number of edges. However, actual degree distribution of the vertices is binomial, that we know, and where the probability that vertex is of degree I is given by Pi is equal to NCI. Pi is equal to P power I 1 minus P power n minus 1. This is the probability which we have for binomial distribution. Now what we will show, that limit of this summation I running from 0 to n, I into I minus 2 into Pi is equal to 0, because according to this Mullian's read says that if lambda is the fraction of the vertices of degree I, then there will be a giant component if and only if this summation of this quantity is greater than 0. So if I can say that, if I can prove this quantity is 0 for this Pi is this binomial distribution that we have. When P is equal to 1 by n. So to prove this one, we'll see what is this quantity. So now we start with summation I running from 0 to n, I into I minus 2, that is into Pi. Into Pi is this quantity, that is NCI, Pi into 1 minus Pi raised to n minus I. Now this we can write down as, by putting the value of P, that is 1 by n to the power I, 1 by 1 minus 1 by n power n minus I. Now let us expand this NCI, that is n into n minus 1 up to n minus I plus 1 upon I factorial. This n power I is already there, and into 1 minus 1 by n power n into 1 minus 1 by n power minus I. So I just separate out this n minus I into this manner. So if we can see that, and we already know that a limit of n tends to infinity, 1 minus 1 upon n power n will be e. No, it is 1 minus n power 1 upon n is e. So here it is 1 minus 1 upon n power n. So this quantity is actually 1 upon e. That is a reciprocal of that as n tends to infinity. So I will take this quantity by taking the limit both sides. So therefore now a limit of n tends to infinity, summation I running from 0 to n, I into I minus 2 into NCI, P raised to I 1 minus P raised to n minus I is equal to 1 upon E, limit n tends to infinity, summation I running from 0 to n, I into I minus 2. So this quantity, it is 1 upon e that we have seen. So the rest of the quantity is as this n into n minus 1 n minus 2 up to n minus I plus 1 upon I factorial n power I n upon n minus 1 I power n. Now this entire quantity, this is 1 of n upon n minus 1. So that we have, this quantity is written as n minus 1 upon n power minus I. Since if I want to change this is, we can just rewrite this as n upon n minus 1. So it is power I. So it is n minus 1 upon n. So that's the quantity is power I is there. So this is the quantity we have. Now, first of all, you just observe this n power I is cancel out with this. And in the numerator, you will have it is 1 upon e limit n tends to infinitive. Summation I running from 0 to n. I into I minus 2 upon I factorial. I just write down here. What is quantity is there? So this is n into n minus 1, n minus 2 up to n minus 1 plus I upon n minus 1 power I. Here there are items. So I'll just write down this quantity as 1 upon e limit n tends to infinitive. Summation I running from 0 to n I into I minus 2 upon I factorial. This I can write down n upon n minus I into n minus 1 upon n minus 1 into n minus 2 upon n minus 1 up to so on n minus I plus 1 upon n minus 1. Now each this quantity which we have here, this is obviously 1, but this quantity that is n minus 1, so n minus 2, we know that n minus 1 is bigger than n minus 2. So that's why n minus 2 upon n minus 1 is less than or equal to 1. So this quantity is less than 1 and the this all the quantity which we have here, they all are less than 1. So finally, what we got is this quantity, entire quantity is less than 1. So for that we can have, so therefore limit of n tends to infinity, summation I running from 0 to n I into I minus 2 into NCI p power I 1 minus p power n minus I is less than or equal to I running from 0 to infinity now, because I'm taking the limit, and 1 upon e is also less than 1. So that's why we'll say it is less than or equal to I into I minus 2 upon I factorial. All this quantity is less than 1. This quantity is also less than 1. So only the quantity is left is this. Now we have to prove that this is equal to 0. So we shall, so that summation I running from 0 to infinity I into I minus 2 upon I factorial is equal to 0. To see this, we'll just see that what is I running from 0 to infinity I upon I factorial. That is summation I running from 0 to infinity. Since 0, if I substitute, the first term is already 0. So that actually starting with 1, I running from I upon I factorial. Because if we substitute the first term I equal to 0, it will be the 0. So this is equal to summation I running from 1 to infinity 1 upon I minus 1 factorial, because 1 I is cancelled out. So left with this. And if I change the index by replacing I by I minus 1, so replacing I minus 1 by I, we start with I equal to 1. So it is actually start with I equal to 0 to infinity, 1 upon I factorial. So that means this quantity is equal to 1 upon I factorial. Why we have seen that? Because it is actually the numerator we have, it is I square minus 2I upon I factorial you have. So that's why it is I upon I factorial that we have seen. That is this quantity. Now it is I square upon I factorial. So now let us see what is I square upon I factorial. And the summation I running from 0 to infinity, I square upon I factorial will gives me I running from 1 to infinity, because again if I substitute 0 here, it will gives me 0. So first term is 0 and 1 I is cancelled out, so it will have I upon I minus 1 factorial. Now will this quantity, by replacing I minus 1 to I, that will gives me I running from 0 to infinity, and numerator will have I plus 1 upon I factorial. To replace I minus 1 to I, so we'll have this. Now this, by partial fraction, we can write down this is I factorial upon I upon I factorial plus 1 upon I factorial. But I upon I factorial we already have concluded, that is I upon I factorial is summation of 1 upon I factorial. So that's why this is 1 upon I factorial plus summation I running from 0 to infinity 1 upon I factorial. So that's why it is 2 times summation of I running from 0 to infinity 1 upon I factorial. So now we will substituting these two values into the this. So now summation I running from 0 to infinity I into I minus 2 upon I factorial will write as summation I running from 0 to infinity I square by I factorial minus 2 times summation I running from 0 to infinity I upon I factorial. But I square by I factorial, we already conclude that it is 1 upon I factorial. So that is 0 to infinity 1 upon I factorial 2 times. And this is I upon I factorial is also 1 upon I factorial. So this will gives me 0. So thus we have here this quantity is 0. So by this Mully and Reed's, we can say that GNP graph model has a giant component when p equal to 1 by n. So this is another way is to looking at the concept, and basically in this example we have used this concept of Boolean read that says that if lambda I is the fraction of vertices having the degree I, then there will be a giant component if and only if the summation of I into I minus 2 into lambda I is greater than 0. So with this uniform non-uniform giant component